Okay. Good morning, everyone. Very privileged that we are starting this up. No pressure. I think you can sit down. So today we're going to be presenting on who wins and who loses. And the model is basically linking up a microsimulation model with a more macro CGE model. Actually, the commissioner and most of the people that spoke before me have done a big part of the job already. So I'm just going to be doing, going into some technical details of why actually this is important. Next slide, please. I can just click something there. Okay. Yeah. So the talk is going to be divided into 3 parts. The first part is going to be honing in on what has been mentioned about the importance of microsimulation and linking that to the CGE model, essentially to try and distill what the macro level effects mean at the individual and the household level. The second part is going to be presented by Natasha. Natasha is a master's student that is working with me. It turns out that she was very brave enough to take on this modeling. So she will be presenting a validation exercise on microsimulation modeling using the COVID-19 pandemic as an experiment. And the third part of the presentation, I will come back and present on the results on the project we did with the PCC that was submitted last year. So I'll give you some summary of the result from that project, linking microsimulation model to the CGE model done by the UCT team. So to start, I'm sure you can see the diagram on the right-hand side very well, but I will explain. I know there are people in this room that know more about CGE models than I do. But the idea is that CGE model are large data incentive simulation analysis that model the entire economy. So the idea is that you have a shock or a policy change in one part of the economy, and that ripples through the economy because everything is affected. So if you have increase in the price of farm produce, for example, if you tax that, it will raise food prices, which might cause workers to demand more wages. And so you see the effect go through the economy. So when something happens on one part, just stay on that part. There's a second round effect and a third round effect down the line. So what CGE model allows you to do is to take a policy or a shock and then see how that affects every part of the economy. In this case, we are interested in the household and the individual part of the economy. However, as has been mentioned by previous speakers, one disadvantage of the CGE model is that it gives you results at the aggregate level. So it may say something like, well, this policy change is likely to increase job in this sector by 5%. It cannot go lower than that. And the issue is that CGE work on what is called representative household. So it's the idea of aggregating household into groups so that you can model them. So you can talk about something like urban skilled household and group everybody that you categorize, you put in that category as one household and aggregate them up. So you can have a few representative households in your analysis. The problem with that is that while you can study differences between groups, you're limited in studying differences within groups. But if you want to be able to say more about where this effect is being felt at the household and the individual level, you have to be able to talk about inequality within groups. CGE model is very useful, gives you an idea of what is happening at the big picture level. But we all know that, based on analysis that have been done in so many places, that often within group differences are more important than between group differences. And you are not able to get to that because you have your result at the aggregate level. So the question is, how do we compare competing policy actions, for example, under the energy transition banner, without knowing what this means at the detailed individual and household level. So it becomes difficult to be able to answer the question about whether the policy you are putting in place is just when you're unable to tell of the welfare consequences at the individual and the household level. Because we all know that the mere fact that GDP is growing doesn't mean that everybody in the economy is doing well. Those growths sometimes are not distributionally neutral. So you want to know where the negative effects are and where the positive effects are, and be able to plan mitigation strategies around that. So that is why the idea of microsimulation modeling is important. So for example, the broader international literature, at least most of them, are very optimistic about the effect of energy transition in terms of creating jobs. Most studies suggest that there will be a net positive in terms of, if you compare job loss with job gains. And that the spending on renewable energy is likely to create more jobs compared to spending the same amount on the existing systems that we have. But this growth may not be distributionally neutral. So for example, in South Africa, we know that transitioning from coal is likely to affect Mpumalanga and then redistribute the benefits elsewhere in the country. You need to be able to understand that to be able to plan effective mitigation strategies. So in the absence of that, you will create deficit, serious deficit in some places, and maybe surplus in other places. And the planner needs to be able to understand that to be able to make the transition just. Without that, it is impossible to talk about just energy transition because you don't have the information that will allow you to balance the scale, so to say. And there has been many examples of this in the literature where studies have shown that energy subsidy reforms, for example, have positive effects on economic growth, but that effect is not distributionally neutral. You need other policies along with that to make sure that you don't create a serious problem in the economy. So the value of linking CGE model to microsimulation model allows you to identify winners and losers on the individual and household level, which is very important. It allows you to be able to do within group analysis and see the heterogeneous effects that will be able to inform policy better. That can lead to better policy targeting because then you know where the policies are needed. And then it allows you to be able to compare different policy actions. So do you want to transition very quickly or do you want to transition slowly? That may often have different implications for poverty and inequality in the society. So you want to have that information to be able to make better decisions. So what is this microsimulation analysis that I'm talking about? So by microsimulation analysis, we mean we project the result from the CGE. So CGE is still very important. We project the result from the CGE onto a survey data set that record information about individuals and the household they live in. By doing that, we can then simulate the counterfactual labor market that the CGE is talking about. But because the model and the survey data come with a lot more information about demographic groups, about the kind of household people live in, you can say a lot more about the details of what that effect mean at the individual and household level. So this idea is not new. The idea of connecting CGE model to microsimulation model is already out there and has been done on various other policy questions, but it turns out that we don't see a lot of it in energy modeling. And this is particularly important in developing country context. Compared to developed country where inequality is low. In developing country, you actually need to understand this stuff to be able to make the transition just. Otherwise, it becomes very difficult to understand the implication of different policy and which one is actually better, given the context you are working in. So like I said, there is a handful of studies even in relating to energy that has modeled this. And again, the result is consistent that often the positive effect you see from some policy is not distributionally neutral. And you need to understand who is getting the raw end of that deal to be able to plan mitigation policies to make sure that things are more just. So essentially, this provides policymakers with a toolkit to better understand the result of the CGE model and to better be able to plan policies to mitigate the negative effects. So the question is, if these models are already out there and being used, why do you need to validate it? By validation, we mean, well, does this model tell us what we think it's telling us? And how good is this model in helping us capture the effect of a shock or a policy change? So it turns out that there are various ways in which you can link a microsimulation model with a macro model. And it turns out that the way you actually link them does matter for the results you get. So literature suggests that the linking, the method with which you link them matter for the result, and the context in which you are studying also matter for the result. So for example, we have linking approaches that is called top-down accounting approach. So the idea is that, for example, the example I gave, if the CGE model says there's a 5% job gain in a particular sector, you generate a random number and you arrange people by lottery, 5% of the people in that sector will lose their job. That is quite different from a linking that accounts for behavior. So for example, you could, and in what we'll show you, you could calculate probability of people being in different sectors. And if the CGE model says 5% of the people are going to lose their job in this sector, then you arrange people according to their probability of that sector. And you remove people with the least probability of being in that sector because they are least attached, because that accounts for behavior. The importance of things like that is like if you look at labor market participation anywhere in the world, men are more likely to be in the labor market. Your micro-simulation model will account for that. So when you are predicting employment, the variable gender there will predict positively for men than women, and that will reflect in your analysis. So you can see how not accounting for all those things can affect the final result you get at the end of the day. So that's why it's important to actually test in a particular context whether the microsimulation model or the approach you're using is actually giving reasonable result. The other thing that is important to mention in this respect is that the other speakers talk about people working in silos. So for example, we are sitting at VITS, and the micro simulation, the CGE model was done at the UCT team. That matters for the way you link it, because there is an approach of linking microsimulation and CGE model where the macro model is run, gives the result to the micro model runs it and gives feedback to the macro model, and you go back and forth until you get some convergence. Now, you can't do that when the two teams are sitting in different universities. That becomes a lot more difficult to do. So we are restricted to the top-down with behavioral approach. So it becomes a very important question to say, actually, the approach we are able to implement, does it give us good results in the context of South Africa and in the context of the question we are interested in? Now is the part for the micro-simulation validation exercise. I'm going to invite Natasha to come and present that part.
Okay. Good morning, everyone. My name is Natasha Dikola, and as we've just heard from Prof. Adiola, understanding the who behind just transition is very critical. A few speakers before me have mentioned that, the CGE model tells us about the macroeconomic impact, but to see the effect on real people, we need a different tool, and that tool is microsimulation. Did I use this one? Oh, okay. Now, while using microsimulation, it is important to note that it doesn't require input from a CGE model. Any well-defined policy shock can be used. And in our paper, we used the COVID-19 pandemic as a natural experiment to validate this exercise. Now, we know that in COVID, there was an increase in job losses and income losses. And because we have access to the 2019 data and the 2020 data, we can calculate those losses, and we'll use those losses as our shock into our model. So what we did was we calibrated the Tiberti, Sikowitz, and Cockburn framework to our 2019 LMDSA dataset, and then we pretended that we're back in 2019. We inputted those shocks into our model and asked our model, can you reproduce the 2020 labor market? So after that, we compared our simulated 2020 data to our actual 2020 data. Okay, so now I'll just briefly walk you through how the model works. So firstly, to simulate the 2020 environment, we need to take into account the changes in population between 2019 and 2020. So what we did was we used a static aging or reweighing approach where we calibrated the 2019 weights to fit the 2020 population data. And in addition to that, we also made sure to match the marginals to the 2020 provincial totals. Then the second step that we did was we calculated our shocks. Now this is just the percentage changes in employment and wages by sector and skill, and we derived that by just comparing like the 2019 and the 2020 data. So what we have next is a visual representation of our COVID-induced shocks that we will be implementing into our model. So the first shock that we're looking at is the percentage change in each sector's total share of employment. So it is important to note that when interpreting these numbers, that they are not comparable across all sectors. For example, when you look at that graph there, you see a negative shock of 7.8% in the other services sector. And when you compare that with the negative shock of 2.3% in the services sector, this does not mean that the other services sector lost more people when COVID happened. No, this percentage change reflects the change in the total share population from 2019 to 2020. So not how many people lost their jobs in absolute terms. Yes. So when you look here, you can see that the negative shock was concentrated between manufacturing, construction, and other services. And you can see that it was the unskilled workers were more affected compared to the skilled workers. Now, when you look at the first two sectors there, the agriculture and the, sorry, I can't see there. The agriculture and the mining sector, you can see that we have a positive shock. This doesn't mean that the sector grew in absolute terms. The agriculture sector actually lost about 42,000 unskilled workers. So the reason for that positive shock could be one of two reasons. Number one, it could be that those two sectors were not as heavily restricted because they were deemed as essential services during COVID. And it could be because we compared yearly data instead of quarterly data, which is something that I think we will look into in further analysis. Here we can see the average wage decline between the unskilled and skilled workers. We can see that for the unskilled workers, there was an average wage decline of 7.1%, and they were more affected than skilled workers, which had a smaller average decline of 3.8%. Now, showing you these visually is what we're going to be inputting into our microsimulation model when we are simulating our 2020 data. So the third step in our validation exercise is our multinomial logic model that governs how people move across sectors in response to these shocks. So each individual, their probability will be estimated based on their characteristics like their geographical location, their gender, their age, their household head dummy, the number of children, as well as the marital status. One thing that I have to mention is that we have 6 different employment categories, and it's either you're in one of those 6 or you are in our base category, which we have defined as unemployment. Now we will look at the microsimulation model for income. So we estimate a Minter type wage equation using the Heckman 2-stage model. And just like what we did in unemployment, we do this separately for skilled and unskilled workers. Then finally, we have 2 key assumptions that structure our labor market. So the first assumption is that we assume perfect mobility across sectors, and the second one is we assume perfect rigidity across skills. So this means that unskilled workers cannot take up skilled work, and skilled workers cannot take up unskilled work. Now we get to the most important part of our microsimulation analysis. So here we will be using a 2-stage queuing algorithm based on the individual's probabilities. So let's say a sector experiences a negative shock. So what we'll do is we'll look at the individuals in that sector, we'll rank them based on their probability of being employed in each sector, then from lowest to highest. So the logic behind this is that the people with the lowest probability of being employed in that sector will be the first ones to move to unemployment. And this percentage reduction will be done until the quota is met. So now if we have a sector that is growing, we will then look at the workers in all the other sectors, including unemployment. We will rank them based on their probabilities of being employed in that growing sector from highest to lowest. And the logic behind this is that the people with the highest probability of being employed in that sector will be hired first until the quota is met. Now, notice that this includes moving people from the previous sector that has satisfied the shock in the previous checking. So now after this, we'll have imbalances in our marginals. So then we will be needing the second round of the queuing algorithm. So this round is used to handle all these imbalances, and that will draw from the unemployed sector alone. So we'll look at the individuals in the unemployed sector, rank them on their probabilities of being in those sectors, and then fill them up just like that. Okay, now we'll look at how the model actually performed. So here you can see that we have the unskilled employment. We're comparing the simulated 2020 to our actual 2020. And the key takeaway here is that the model performed relatively well. So 6 out of the 7 simulated employment shares actually fell within the 95% confidence interval of the actual 2020, except for unemployment where the model predicted 42% unemployment with the actual upper bound of 41%. When we look at the skilled employment, we see a different story. We see that for 7 out of the 7 sectors, all the simulated employment shares fell within the actual 2020 95% confidence interval. Okay. The wage validation shows a more nuanced picture. So for unskilled workers, the simulated average wage of 19,930 falls comfortably within the actual 95% confidence interval. But when we look at the unskilled workers, we have a slightly different story. We have a simulated wage of 7,951, which is just R1 above the actual upper bound of the confidence interval. We also looked at the kernel densities. So now when we're looking at this, we see that the simulated and the actual wage distribution shape is nearly identical in shape, spread, and in tail. The only deviation is the peak of the actual 2020 data, which is slightly higher. But more analysis on this will be done. I think we were doing that yesterday. And then when we are looking at the skilled workers, we see that it is more pronounced. But yeah, as I said, more analysis will be done regarding this.
Thank you, Natasha. Just a big background. Natasha did this for our honors project, which was very brave of her. I did offer it to the master's student. All of them chickened out. Yeah. So now I'm going to be rounding up by presenting some of the results from the project we did with the PCC. So the project is actually separated into 3 parts. One part of it looked as skills you need for transition. The other part look at the importance of having social assistance as a strategy to support the transition. And both of those papers refer to the results that I'm going to present to you now, which talks about the simulation exercise that try to distill the CGE result into the microsimulation model. We did have a lot of discussion with the PCC on the scenarios to select. I'm sure both of us didn't get what we would like, but we landed somewhere in the middle. So these are the scenarios we selected. What we set out to do ideally is to see the effect of different energy caps on jobs and inequality. So we selected 8 gigaton, 10 gigaton, which the PCC regard as business as usual because that will happen anyway. And then we have 9 gigaton and 8 gigaton to compare with that. We have some other parameters there that I will not go into, but they are just additional assumption that is used in the CGE model to produce the result. So unlike the validation exercise, I need to tread carefully and explain how some of the assumption of the microsimulation model might be a little bit problematic, depending on the way you look at it. So the result Natasha presented was about 2019 and 2020, right? So those years are reasonably close to each other. And we all know that the more you stretch these things out, the more you kind of accent too much of the data. So in this analysis, we're stretching it out to 2050. But yeah, I'm going to give you the result, the important part of the results. You can take the later years with, well, you can be skeptical about the later years because it's likely to be more accurate in earlier years. In terms of what we did with the population, we follow what the CGE modelers did by using the United Nations population projections. So basically, like Natasha explained, you basically calibrate the way to fill the population estimates in future so that you account for that population growth in your model. The problem with that is that that assumes that your ratios of different demographic characteristics do not change over time. Now, that's a more reasonable assumption in the short term rather than the long term. So again, you have to be careful about the way you interpret the result as you go further into the future. In terms of the shocks, the shock came directly from the result of the CGE model, and this is what they look like. They're actually models the earlier part of COVID into the analysis, and then you can see positive shock there. So one of the important assumptions that I forgot to mention here, if you look at it, is the growth rate assumed in the CGE model. This is what I mean that we had a lot of discussion with the PCC on that. We felt some growth rate over-optimistic. They felt our suggestion super pessimistic, so we landed somewhere in the middle. In terms of the way the model works, is exactly the same as what Natasha explained, only we have smaller number of sectors here, 5 sectors, with the last one being the unemployment sector. So the way the model works is exactly the same thing. We use the Mincer type equation to predict wages. So essentially what happened is that the macro model will tell us what the size of the shock is. We put the size of the shock into the model and use the probability of individuals to determine who is moving out of employment and who is moving into employment and into what sector they are moving into based on their probability. So that's accounting for behavior that you will not be accounted for in just using random number to determine it. Then we assume that there is perfect mobility across sectors. So people can move from mining sector to agricultural sector and vice versa, but they can move across scale. Now, the definition of our scale is very crude. It's metric and higher scaled. Below that, you are unscaled. It's easy to implement, but we know that that's a bit crude. And we're looking for improvements in that front. Perhaps we'll talk about that later. And so just like Natasha explained, the queuing algorithm makes sure that people that have the highest probability of being in a particular sector end up in that sector, provided that that satisfies what the CGE is saying in terms of the amount of individuals that should be in that sector. And then we do that across all the sectors. And by doing that, you have simulated a counterfactual labor market where the shock has been realized. And conditional on that, you can then use the other model to predict the wages for those people that are not employed. So the people that are employed there might be different from the people that are employed in your baseline. You need to predict wages for them based on their characteristics. Now for the results, just to show you what is coming out of the CGE model. So that graph is just showing you what comes out of the CGE model directly. And immediately you will notice that what we set out to achieve becomes a little bit problematic because there's not a lot of variation between the different energy caps. If you look at 8 gigaton, 9 gigaton, and 10 gigaton there, they kind of follow each other closely. So we don't get a lot of variation there. We start getting the variation when we vary the GDP assumption. So the high growth rate of 3% versus the medium growth rate of 1.5% start showing you divergence in the transition of employment prediction in the CGE model. So what that means is that what we originally set out to achieve, which is figure out how energy restriction affect the economy, is turning out to say, well, actually, the answer depends on what your the growth rate you are assuming from the economy will be, because all that is washed out by what the growth rate is doing. Now for the result, for me, this is the most important part of the result. So you will see a couple of lines there, and some go all the way down to the end of the period we're looking at. And there is that blue line that stopped right in the middle. What happened there is something that took myself and the team months to figure out, but then we finally figured it out. So what happened is that, remember that assumption where people cannot move across scaled category. It turns out, unsurprisingly, in South Africa, you have more people in the unskilled group than in the skilled group. Now, remember the graph that shows increase in jobs as a result of transition. What happened is that as you go along that graph, you run out of skilled people to fill the skills jobs that are being created in the economy. And then the model just breaks down at that point. So in order to be able to run the model to the end, we have to relax that assumption and allow people unskilled to move into the skilled category and get jobs. And that's only when they are. And that gets worse the higher the GDP growth rate you assume. So if you assume high GDP growth rate, that will happen earlier. If you assume low GDP growth rate, that will happen a bit later. So that turns out to be a very important result because it tells us something about what the South African labor force looks like. So let's take it that we agree that there will be high job growth as the literature predicts for energy transition. It means South Africa might not be able to realize that if you don't have a good skills strategy to back up the transition. And this is the importance of the microsimulation model, because the CGE model was able to overlook that. But when you come to actual individual and household and you take behavior into account, it tells you that this will not actually work given what you have in your labor market right now. You don't have enough skills people to fill these jobs. So there will be a problem at that point in time. And this is why when I said the result might depend on the way you actually link, going back and forth, because ideally what's supposed to happen is we say, well, guys at UCT, this is not going to work because of this. You need to go back to your assumption and check it again, and then we go back and forth, but we don't have the infrastructure to do that right now. So for me, that's one of the most important results. Of course, because of the increasing creation of jobs, the Gini coefficient trend downward in all the analysis. Another thing that is important is that we now compared the distribution of income as time goes on, right? And we're able to do this to the end because we relaxed the skills restriction. What you will notice there is that towards the bottom end of the graph in year 30, you start having a case where, so this is called the relative density approach, where you compare two densities, and if the mass at that base in both densities are the same thing, you get a value of 1, so you get a uniform distribution. If the numerator density has more mass than the numerator density, you have a value greater than 1. And that's what you can see at the bottom end. What that means is that, remember the skills restriction that we relax, allowing unskilled people to get skilled jobs. It turns out that when you do that and you want to predict the income for those people, because of their characteristic, you predict low income for them. And then that's why you have that at the bottom end of the distribution. Again, that is important because it tells you that even if you are able to somehow employ these people, it's going to end up clustering them in the lower end of the income distribution because of their characteristic, emphasizing the importance of skills intervention. So just to wrap up, this is the unemployment transition that is shown in the model. You see unemployment trend downward because of the high growth rate in jobs. And that is mostly driven by, I didn't include that slide. That unemployment is mostly driven by women, young workers, and people in the agriculture and the mining sector are the ones driving most of those unemployment. So even when the overall outlook is positive, you have the tendency to leave some people behind with certain characteristics in there. And that is important to be able to plan mitigation strategies. In terms of future work, we think we can extend the validation exercise to cover more years rather than comparing 2 years that are adjacent to each other. We spoke about replacing the likely econometric model with machine learning models, since those are built for prediction and they perform better out of sample. You remember what we're basically doing when you create a counterfactual world is that we are predicting income and employment out of sample. So those machine learning models are likely to do better than the current models that we're using. We can use quarterly data for the validation exercise like Natasha mentioned. And we have a collaboration with Prof. Rula and Prof. Ehrenreich at UP to do more work in relation to this regarding the RIP5 that was just released. So in conclusion, for me, the most important part of the results is that there is a need to think about skill strategy to be able to take advantage of the jobs that will be created if all the prediction in the literature materializes. We need job skills development to be able to actually benefit from that. We argue that the methodology is likely to yield more insight if you are able to get more variation between the energy cap scenarios, because what we are picking up here is being driven by the GDP assumption. we think the real value in microsimulation analysis is being able to tell us how to compare different policy scenarios so that we are able to make decisions that are just, which is the entire point of this whole thing. Thank you very much.